Log on, tune in, find out. Another good idea from Cambridge.
Be here, it's my first time. So that's my title up there. Let's slowly start. So maybe before starting, I'll give you a short outline of the talk. So I'll start by recalling or defining what are isoperimetric inequalities, and then I'll do the same for concentration inequalities. Certainly I try to recall what these inequalities are useful for, and then we'll be able to state our main results which connect between these two different types of inequalities. Okay. I hope I'll have time to give you some brief idea of the proof, but certainly I'll try to save some time to speak about a sample application of these main results, which would be an application for the stability of the spectral gap or log Sobolev inequality. I'll explain exactly what I mean by this. And towards the end, I hope I'll have time to speak about something new related to compact Riemannian manifolds with density. Okay, so let us start slowly. So here's the notation which I'll be using throughout the talk. So omega d mu will always denote a measure metric space in the notation of Gromov. So this just means that omega is just a set. D is a metric on this set, let's say complete, separable. And mu is a Borel measure on this metric space. Okay. Now, just to have a concrete situation in mind, if you like, you may just imagine that omega is some subdomain of an n-dimensional Riemannian manifold. Let's say nice manifold, smooth, connected, oriented, complete. Okay, and that d is the our metric is given by the induced geodesic distance on this manifold. Okay, just connecting via geodesics. And that our measure mu has a density with respect to Riemannian volume form at omega. Let's say the density is nice, smooth, h. Okay. So isoperimetric inequalities compare between the measure mu of some Borel set A and some notion which tries to capture the boundary measure of the set with respect to our measure mu and the metric d. And the notion which we're going to use here is the so-called Minkowski's exterior boundary measure, which we denote by mu superscript plus of A. And here's the definition. Okay, so we take our set A and we take its epsilon neighborhood, of course with respect to our metric. We take the measure of this epsilon neighborhood, subtract the measure of the original set. Okay, at this point we get this measure of this strip which is marked in green. We divide by the width of the strip, epsilon, and take the limit inferior as epsilon goes to 0. Okay, and if one thinks about this for a few moments, one realizes that this is indeed a very natural generalization of the usual notion of surface area from our more familiar Euclidean or Riemannian setting. Okay, let me just remark here that notice that if omega itself has a boundary, then this notion only captures the part of the boundary of A which lies in the interior of omega, okay, not this part. Okay, and having this notion of boundary measure at hand, it's convenient to introduce the following very useful function called the isoperimetric profile of our space, which I'll always denote by this letter I. And here's what it does. It takes a real number v in this interval between 0 and the total measure of our space, okay, and gives back its value, I of v, which is just equal to the infimum over all boundary measures of sets having measure exactly equal to v. Okay? So in other words, the function I just serves as the best possible lower bound on the boundary measure of a set as a function of its own measure. Okay? We'll see an example in a second. But before going to the example, maybe let me just remark already at this point that typically for under very mild assumptions, which will always be the case for us, and for a generic set A, the boundary measure of the set will be equal to the boundary measure of the complement of the set. Of course, the set and the complement share the same topological boundary in the interior, but this doesn't necessarily mean that they're going to have the same boundary measure, because remember, we're taking limits from the exterior side. And the exterior side, when we switch from A to the complement, may be different. In principle, the limits could be different, but under very mild assumptions for generic sets A, it will be the same. And therefore, the point I want to make is that if, for example, the total measure of the space of our space is finite, in which case I could just renormalize and assume that it's equal to 1, then automatically this symmetry property will be inherited by the function I. So I, the point 1 minus v, is going to be equal to I at v, simply because we can just look at the complement of the set. I take its boundary measure. So it's just symmetric about the point 1/2. Therefore, whenever we talk about isoperimetric inequalities under this assumption of total measure being equal to 1, it's just enough to talk about sets having measure smaller than 1/2. If we have some other sets with measure bigger than 1/2, just look at the complement. You take its value measure. So I can just imagine that my function I is defined on the interval 0 to 1/2. Okay? And if you want to see what happens on the complementing interval 1/2, 1, just mirror image. Okay? Okay, so let's see an example. And the example is, of course, the classical isoperimetric inequality in Euclidean space Rn. This is my notation for Euclidean norm, which we equip with the just usual Lebesgue measure. And then the statement, classical statement, apparently known to the ancient Greeks, at least in dimension 2, and of course they believed it should be the same in all dimensions, is that Euclidean balls minimize boundary measure among all competing sets having a given volume, given Lebesgue measure. Okay, a rigorous proof of that had to await the 19th century, people like Steiner and Schwartz. But let's see what this means in terms of the function I. So this means that I of v is equal to v, which is raised to this power. And this power, so v is our volume of our set. We raise it to this power because we need to take into account the different homogeneity degrees of volume, which is homogeneous with respect to with degree n with respect to taking homotopy, and surface area, which is homogeneous to degree n-1. Right? So we raise it to this power and multiply by an explicitly computable constant, which just is intended to give the right answer for Euclidean balls. Okay, and that's how this function looks in Euclidean space. Of course, so I apologize for this wiggles. I don't know how to correct that. So of course, there are other solutions to the isoperimetric problem, which are known in other spaces. So for example, we can take a look at the n-dimensional sphere, equip it with its geodesic distance, and use the Haar measure on the sphere. And then it's a classical result from the 20th century by Polevy and by Schmidt. In this case, geodesic balls are isoperimetric minimizers. So that means among all given sets among all sets on the sphere having a given spherical volume, geodesic balls about any point minimize spherical surface area. Okay. Here's another space. In both the other examples, we were using the Haar measure on the space. So here's a space where you use a different measure. So just take usual Euclidean space and endow it with a standard Gaussian measure. Okay, and then it's by now a classical result due to Sudakov and Cyrulson, and also independently Borel from 1970, that in this case, actually, half spaces are minimizers. So among all sets having a given Gaussian measure, okay, half spaces, which are just everything which is to one side of a hyperplane, half spaces minimize Gaussian boundary measure, right? So now you have to integrate the Gaussian density along the boundary of this half space, along this hyperplane. Okay, so everything is with respect to our measure and metric. And there are some other spaces for which the solution is known, like hyperbolic space, and so on. However, the isoperimetric problem, which is just identifying this function I, or sometimes stronger, we would like to actually identify the isoperimetric minimizers, so the sets on which this boundary measure is actually minimal. There are various spaces which seem very naive, very simple, but still we don't know the answer. So my favorite one is the three-dimensional cube, okay, which we endow with the usual Euclidean distance and take the Lebesgue measure restricted onto this cube. Okay, and here, this seemingly naive space, the solution is not known in general. Okay, of course, there are some conjectural minimizers. There's conjecture by Imre Lieder and Bela Bolobash that what the conjectural minimizer should be for this case, but it's not known for all values of volumes. Okay, for all values of v between 0 and 1, it's not known. Okay, if you think the difficulty lies in the fact that the cube has this kind of annoying boundary with corners, then you can impose periodic boundary conditions, look at the three-dimensional flat torus, okay, and still the solution is not known. Of course, in the beginning, it has to be a ball, okay, until you hit the in radius of this flat torus, and after that, things become less clear, and so on. Okay, so this list is just meant to kind of convince you that the isoperimetric problem itself is rather difficult, And therefore, this talk we're just going to be content in having good lower bounds on our isoperimetric profile I. And any such lower bound we'll call an isoperimetric inequality. Okay? So why are isoperimetric inequalities interesting or important, besides from their inherent interest in geometry? Well, one answer is that they are connected to some other types of inequalities which one may care more about, like Sobolev inequalities, which you all learn what these are, and if we don't remember, I'll recall in a second, and also concentration inequalities. Okay, so maybe these are slightly less well known, so let me start by recalling what are those. So concentration or large deviation inequalities, well, these only make sense when the total measure of the space is finite, in which case I can just renormalize and assume that the total measure is equal to 1. So mu is a probability measure. Okay, and this is exactly this type of statement. So this is a statement of the following form. So for any, we would like to require that for any Borel set A having measure at least 1/2, if we take the extension of this set by a distance of r, and we take a look at the measure of whatever is left outside in the complement, this has to be bounded from above by a function k depending only on r, uniformly for all such sets A. Okay, and hopefully this function, as r goes to infinity, should decay to 0 at some prescribed quantitative rate. Okay, so in other words, this is just quantifies how tightly the measure mu is concentrated around sets having measure 1/2, right? If we start with any such set and we take the extension of this set, we want to say that there's not much left outside in terms of measure. Okay, this is the so-called concentration of measure phenomenon. And this concentration measure phenomena or concentration inequalities have been used for a long time. One of the very first instances was in Banach space theory, say by Emanuel Milman, would later evolve into asymptotic geometric analysis, but it has been used in many other fields like probability analysis, mechanical physics, graph theory, combinatorics, and so on. Okay. So these are pretty useful inequalities. Let me, at this point, already emphasize that by their very definition, okay, these inequalities are only meaningful in the large whenever this extension R is big enough, okay, by definition. And in particular, they do not provide any infinitesimal information about infinitesimal extensions, extending by a small amount, very much to the contrary to isoperimetric inequalities, which are all about infinitesimal extensions. Okay, so these are really different types of inequalities. How do we see this from the definition that they are only meaningful in the large? Well, notice that this left-hand side of this inequality, this is the measure of a set, of the complement of a set having measure at least 1/2. So of course, the left-hand side is smaller or equal to 1/2. Okay, obviously. But I never required that k of r has to start at 1/2. K of r, when r is close to 0, could start off very big, like 100. Okay, and at this point, the inequality is, of course, meaningless. And only at the first time, the first value of r, when k of r drops below 1/2, does this inequality become meaningful, non-trivial. Okay, so this is how we capture the fact that these inequalities only make sense in the large. Okay, it's really different from isoperimetry. One last comment is that we can just, useful for later on, instead of talking about sets, we can completely equivalently reformulate these types of inequalities in the language of one Lipschitz functions. Okay, so this is completely equivalent to saying that for any one Lipschitz function on our space, with respect to our metric D, the measure of all points x where f deviates more than r from its median with respect to mu. So the median is just a value so that the sub-level set of f corresponding to that value has measure, let's say 1/2. Okay, just what you expect from the median. Okay, so this measure where f deviates more than r has to be bounded from above by k of r. Okay, it's exactly the same, just by passing from functions to level sets using the one Lipschitz property. This is exactly the same as looking at extensions with respect to our metric. Okay? Okay, so what is the connection that I mentioned earlier? Usually there's some hierarchy, actually. You can arrange these types of inequalities in some sort of hierarchy. So usually isoperimetric inequalities imply some sort of Sobolev inequalities, which in turn usually implies some sort of concentration inequalities. So here I'm just reminding you the definition of concentration. Let's see this by means of examples. Okay? So the classical example or classical result from 1960 due to Federer Fleming and also independently Mazia is that a Euclidean isoperimetric inequality, this is just what we saw, right? This function we saw, is just equivalent to the following Sobolev inequality relating between the L1 norm of the gradient of a nice function f, let's say smooth with compact support on our end, and the Ln over n minus 1 norm of f. Okay? It's equivalent in the sense that the best possible constant here is just equal to the best possible constant here. Okay, so that's classical result, and already we see the relation between geometry and analysis. Now, Euclidean space doesn't have finite measures, so concentration inequalities don't make sense. Okay, so let me not speak about those here, and let's move on to the next two examples which are more relevant for this talk. Okay, so here's an example. Let's assume now that the total measure of the space is equal to 1. So mu is a probability measure. Okay, so one type of isoperimetric inequality is a linear isoperimetric inequality. So I of v, when v is between 0 and 1/2, is bounded from below by some linear function of v. Okay, by their very definition, this is exactly how expanders are defined, having a linear expansion property. Okay, just to give you, this is a discrete workshop, right, semester, so I have to say something in the discrete setting. But more relevant, maybe for us, is this example of Euclidean space Rn endowed with a log concave density. Okay, so a density, a function f is called log concave if it's of the form exponential of minus v, okay, where v, let's allow it to attain plus infinity, is convex. Okay, so exponential of minus convex we call log concave. The logarithm is a concave function. Okay, so examples are, for example, the Gaussian density, right, e to the minus quadratic is log concave, and also a uniform measure on convex sets is a log concave measure. Okay, uniform on convex sets, it's also an example. So in these cases, it's known that there always exists such an isoperimetric inequality. And now by a classical result of Cheeger, so-called Cheeger's inequality, which is also independently proved by Mazia earlier, this always implies a linear isoperimetric inequality always implies a Poincare or spectral gap inequality, which relates between the L2 norm of the gradient of f and the L2 norm of f after we center it, after we remove the integral with respect to mu. Okay? And if the constant here is d, then it's known that the constant here you can write is d over 2. And this factor of 2 is sharp. You cannot improve it. Okay? So this is a one-sided relation now. And now it's also known by result of Gromov and Vitaly Milman that Poincare inequality always implies an exponential concentration. So now this function k of r, we know it will decay like e to the minus r times d, the same constant d here, times some c. So whenever you see a constant, these will always be denoted by the letter c. It's just some numeric constant, like 1 over 10 or 100. The point is that this is just a number independent of any other parameter, and in particular, independent of the dimension. Okay? Just some number whose value I didn't bother to calculate. So that's one example. Let's see a second example, which would be relevant for this talk. This is an example when we start with the space, for example, with a Gaussian space. We said that we know the solution to the isoperimetric problem in the Gaussian space, so I can really write a formula for this, what this function I is, but we're only going to be interested in the asymptotic behavior of this formula. So, and if you work out the asymptotics, it turns out that on the interval 0 and half, it looks like v times square root of log 1 over v. So a tiny logarithmic improvement over the linear case here. Tiny logarithmic improvement. Then it's known that this is an argument of Ledoux, also refined by Bill Beckner. It always implies so-called log Sobolev inequality, a strengthening of the Poincare inequality, which relates between the L2 norm of the gradient of f and something having to do with the entropy of f squared. So I'm not going to define what the entropy is. It's not going to be used in this talk. Let me just remark that these were introduced, this type of inequality was introduced in the 70s by Leonard Gross and actually also independently by Federbush. And they've been very successfully used in probability, mathematical physics. Villani used them in his work. Actually, surprisingly, Perlman used them in his work on Poincare conjecture. So useful inequalities. And lastly, it's known by an argument of Herbst that this always implies a Gaussian concentration inequality. So now k decay is like e to the minus r squared. Okay, so notice here that even a tiny logarithmic improvement on the isoperimetric level leads to a dramatic improvement on the concentration level. And this is exactly why we're going to care about logarithmic factors on this level later on. Okay, so logs are important. Now, I'm not explaining to you why these implications are true. I don't have enough time. But actually, it's easy to see that isoperimetry directly implies concentration, right? Because what is an isoperimetric inequality? It's just an ordinary differential inequality, right? It says that if you take an extension by epsilon and take the derivative with respect to epsilon, you have a lower bound. So if you start with a set and you integrate out this differential inequality, well, of course, you'll just get a lower bound on big extensions, which is exactly what we call the concentration inequality. So just by integration, this always implies that. Okay? Now, the starting point of our work is that all of the reverse implications that we see here are in general known to be false. Okay? So these are really three different types of inequalities, different types of ways to measure the interplay between the measure u and the metric d. And if you look at the counterexamples to these reverse implications, the typical counterexample will always have some bottlenecks in the space, either in the geometry of our metric space or bottlenecks in the measure itself. Okay, let's see just how this looks in terms of the pictures. So here's a space where the geometry has some bottlenecks, right? And here's a space where the geometry is trivial, just a real line, but we see that this density, which just look at the red density here, this density has a very narrow bottleneck here in the middle. Okay? So let me explain why the reverse implication cannot be true on this space. It's exactly the same in that space. So I claim that notice that this space is compact, right? And I claim that for any compact space, we have always a great concentration inequality. Because if we start with any set, and we extend this set beyond the diameter, take a big extension, having the diameter, there's nothing left outside, right? So the measure is equal to 0, and this is the best possible concentration inequality you can imagine, right? Nothing is left outside after a certain extension. So compact spaces have great concentration inequalities, but nevertheless, this space has a very bad isoperimetric inequality, because if you take a look at this kind of bead, having measure 1/3 roughly, then its boundary measure here is just very small. And by pinching this bottleneck, we can make it arbitrarily small. So the isoperimetric inequality is arbitrarily bad. So good concentration, arbitrarily bad isoperimetry. So no possible reversal. And this kind of toy example tells us that if we want to obtain isoperimetric inequalities, it's therefore always a good idea to try to control some curvatures, to impose some curvature lower bounds, or to impose some type of weak convexity conditions that would prevent the existence of these examples. This is by no means convex, and neither is this. Okay, so we need some notion of convexity. Okay? So from here on, we're always going to talk about the Riemannian setting. Okay? We have this nice manifold. We have the geodesic distance on this manifold. If we want, we can take our domain to be a subdomain of this manifold, but then we're going to require that this domain is geodesically convex to prevent these types of pictures. Okay? And we're always going to assume that our measure is a probability measure, having mass equal to 1. So here are some classical results in the case that some type of curvature is strictly positive. Okay? So the classical first kind of breakthrough result was due to Gromov in 1980, so-called Gromov-Levy isoperimetric inequality. And it deals with a case when our measure has constant density, just usual Riemannian volume. But you see this still, that this just means that we normalize to get a probability measure. Okay, we just normalize. Then the Gromov-Levy theorem states that under an appropriate lower bound on the Ricci curvature of our manifold, Ricci curvature has to be bigger than lambda, where lambda is some strictly positive constant. Then, for this space, the isoperimetric inequality is at least as good as that of the n-dimensional sphere, whose radius we choose so that its Ricci curvature is exactly equal to lambda. So this is a sharp isoperimetric inequality where we actually have a model space we can compare to. The model space in this case is the sphere. Okay, so really there's a model space to compare to, and without any further information, you always obtain an isoperimetric inequality. Now, if you're not big fans of manifolds, then let me just comment that Ricci curvature will not be essential for the sequel. And also, let me just give you a very vague explanation of what this means. So basically, Ricci curvature tells you how n-1 dimensional volume elements vary along geodesics. Okay, so in Euclidean space, we can all calculate, if we take some geodesic, we take some n-1 dimensional volume element, and we see how it grows along geodesics. We can all do the calculation. On spherical space, though, if you take this geodesic, this is 3 geodesics, you take this volume element, it'll actually grow slower than what happens in Euclidean space. So this exactly is an indication that Ricci curvature is positive. And in hyperbolic space, it'll actually grow faster. So this is an indication that Ricci curvature is actually negative. Very vague explanation. Okay? Now, this Gromov theorem, Gromov-Levi theorem, was generalized by Bakri and Ledoux in the 90s, and also there's a very nice geometric proof due to Frank Morgan. And now we can actually deal with a case where our manifold is equipped with some density, with some measure having a density of the form exponential of minus psi. Okay, for this case, we need some generalization of Ricci curvature, which is a pretty hot topic by itself nowadays. Generalizing what Ricci curvature means from manifolds to an arbitrary measure metric space works by people like Sturm and Loton Villani. But in the Riemannian case, when we have a manifold equipped with a density, actually it's well known what the right generalization should be. This is a consensus. So this goes back to at least Bakri and Emery, and actually maybe Lishnerovich. The right generalization is to take the Ricci curvature, which is a 2 tensor, and add to it the Riemannian Hessian of this potential psi as a 2 tensor. Okay, and then the requirement that this has to be bigger than strictly positive lambda. And in this case, the right model space to compare to turns out to be just the real line equipped with a Gaussian measure having variance equal to lambda. Okay, so in both these cases, strictly positive curvature means that you have a model space to compare to. Okay, now life is good when curvature is strictly positive, but what happens if it's 0 or even negative? Let me call this minus kappa. What if this is our curvature lower bound? Turns out that in this case, there is no model space to compare to. We'll get back to this point at the end, hopefully. So we need some additional information in order to obtain some type of isoperimetric inequality. In other words, without any additional information, the isoperimetric inequality on this type of space will be as bad as we want. It's easy to construct examples. So we really need some additional information to obtain an isoperimetric inequality here. So let's see what type of additional information has been used in the literature. So the approach in the 70s and 80s by the Riemannian geometry community, people like Berard, Bessot, Gallot, Lee, and Yao, was to impose some upper bound on the diameter of the space. Okay? But this prevents us from considering densities like the Gaussian density, which is not compactly supported. Right? We want to also treat the case of a Gaussian density. What's wrong with that? Another type of condition which was considered is so-called integrability condition. Okay, so this is the assumption that the integral of some function, depending on the distance of a typical point x, typical, I mean drawn according to the measure mu, a typical point x from a fixed point x naught, this is the assumption that this integral is finite. So this is somehow saying that the typical diameter, taking into account the measure mu, is finite. So a generalization of this. This is the type of assumption that has been considered by people like Kana, Lova, Shimonovich, Wang, Ko, Frank Barth, and Kolesnikov. And under either of these assumptions, yes, it is possible to obtain isoperimetric inequalities. The problem is that you always obtain dimension-dependent isoperimetric inequalities, meaning depending on the dimension of our space, and that's very bad for applications. And that's actually an inherent property of either of these assumptions. It's inherent because it's not hard to show that under this curvature lower bound and some reasonable assumption, this distance of a typical point x from a fixed point x naught will always be dimension dependent. So if that's your data, anything depending on this parameter will also be dimension dependent. There's just no way to avoid that. Okay? So this is inherent in these types of assumptions. So let's maybe try to think of some other initial assumptions that will enable us to deduce dimension-independent isoperimetric inequalities. And recall this hierarchy that we just saw, and if you see this hierarchy, it makes perfect sense. It's very natural to maybe start with one of these guys and try to work your way up the hierarchy, reversing the hierarchy. So the first person to do this was Boozer, to successfully start with the Sobolev level and go up. And this was Johns by Ledoux, and we've also had some contribution in this direction. And the good news that, yes, you can go up the hierarchy here, reverse this implication, and obtain dimension-independent isoperimetric inequalities. Okay? But if you see this diagram, then you might as well already start with the weakest level, which is with concentration inequalities. And that's precisely the main topic of my talk, which is that we indeed managed to start with the weakest level and obtain a full dimension-independent hierarchy reversal, closing this implication and rendering all of these three different levels just equivalent up to dimension-independent constants. Okay, so try to state our results now and then talk about applications. So our standing assumption is always that we always have this curvature lower bound. Okay, and we're going to distinguish between two cases. The first case, which I'll call the convex case, is when kappa is equal to 0. Okay, and this is actually an easier case we can see more about. And the prototypical example to think of is Euclidean space endowed with a log concave density. Okay, just in this case, Ricci is 0, and this just means that the potential psi is convex. So the measure is log concave. And the second case is when kappa is strictly positive, so we may have a negative lower bound. I'll call this the semi-convex case, and the typical example is Rn equipped with this double well potential measure, but this curvature lower bound is telling us that the double well cannot be too steep. We have some control over curvature. Okay, so let's see our results. So let's start with the convex case. Okay, so the first result is that the weakest possible concentration assumption that at least I can imagine always implies, in the convex case, a linear isoperimetric inequality. Okay, and we said that always, without any convexity assumption, linear isoperimetry always implies exponential concentration. That's always true. Okay, so convex case has this nice kind of property that the weakest concentration automatically gets upgraded to exponential concentration. Okay, and let's see the precise result. So this formulation, this recent formulation, is actually sharp with respect to all possible parameters. So let me do that. So assume that you have two constants, lambda naught, which you should think of as being slightly smaller than 1/2. Okay? Another constant, r naught, which you might think of as being very large. Okay? So that if you start with any set A having measure at least 1/2, and you extend this A by r naught, it could be a very big extension, and you look at the measure of the complement, then the only thing you know is that this is slightly smaller than the trivial bound of 1/2, smaller than lambda naught. Okay, but uniformly for all such sets A. Okay, so just 1/2 minus tiny epsilon. Then already in the convex case, you can deduce that you actually have a linear isoperimetric inequality, and this coefficient here in front of the linear function as a function of lambda naught and r naught is actually best possible. Okay, it's easy to construct examples. Okay, so we have this property in the convex case. Let me try to convince you maybe that this could be useful for various things, and for this, let me reformulate this result in the language of what I'll call here PQ Poincare inequalities. Okay, this will be maybe more appealing to people more into analysis. So a PQ Poincare inequality is just a relation between the LQ norm of the gradient of f and the LP norm of f after we center it, f. So let's subtract the median, or we could subtract the expectation. It's just the same up to a factor of like 2 or 3. You could do either. It's completely the same. Okay, and let's call the best possible constant in this inequality dpq. Okay, so here's some facts to get us started. So turns out that the 1,1 inequality, when p is equal to 1, q is equal to 1, is just the same. It's completely the same as a linear isoperimetric inequality. Okay, just by passing from functions to level sets using the so-called co-area formula, it's not hard to show that it's the same. Okay, so 1,1 is linear isoperimetry. 2,2 is the usual classical Poincare inequality, the usual spectral gap inequality. And we said that by Mazian-Shiger, 1,1 always implies 2,2. And it's known, it was known by Boozer and Ledoux prior to our result, that in the convex case, 2,2 implies back 1,1. So 1,1 and 2,2 were known to be equivalent. But now, let's try to start with the weakest inequality of them all, which would be the 1 infinity inequality. It's the weakest just by Jensen's inequality. Of course, you can make P smaller here and Q larger. By Jensen, you're just getting a weaker and weaker state. So if you start with the 1 infinity inequality, well, if you're looking at the L infinity norm of the gradient of f, you're just looking at Lipschitz functions, right? So basically, you're saying that you have an L1 bound on centered Lipschitz functions. But that's just equivalent by Markov's inequality, essentially equivalent to saying that you have some estimates on the tail decay of f away from its center. And that's precisely what we called a concentration inequality, an estimate on the tail decay of f after you center it. So actually, the 1 infinity inequality here is some sort of weak concentration inequality. But we just said that weak concentration automatically implies linear in the convex case. So 1 infinity actually implies 1, 1. And from 1, 1, you can actually pass to all the other guys, to all the PQs. So it turns out that the theorem implies that in the convex case, all of these PQ inequalities are just equivalent. They're just the same. And that's pretty useful because if you want to prove a spectral gap estimate, that's a very common task in many fields. Well, instead of doing the 2-2 case, it's just enough to prove a much weaker bound, the 1 infinity case. You just need to bound the L1 norm of centered Lipschitz functions. Okay? And that has been used by various people to indeed give some spectral bounds in situations where convexity happens, where you're in the convex case. So again, we're in this discrete analysis semester, so I have to say something. One last thing about the discrete case. I think this might be an open problem. Find conditions on a graph so that this analogous statement to this statement holds. Okay? Of course, saying that a graph has some spectral gap means that you're saying that it's an expander. Okay? The 2, 2 is equivalent to 1, 1 for a bounded degree graph. Okay? But maybe you can actually test for a certain family of graphs whether this graph is an expander just by looking at Lipschitz functions defined on the vertices of this graph and just bounding, let's say that the function is centered, has expectation equal to 0. You just want to bound the L1 norm. And if you can do that, you say, okay, this means that this graph is an expander. Okay, that would be a much easier test for some. This is definitely not true for all graphs, but maybe for some specific subclass of graphs, which would then, in my opinion, would deserve the name convex graphs. So there are some notions by Jan Olivier with his Ricci curvature of our graph, but I don't know what the solution here should be. Okay. Okay, continuing on with the convex case. So we've seen that weakest concentration always implies a linear isoperimetric inequality and hence exponential concentration, automatic upgrading. But the next natural step is to say, okay, what if you a priori know that actually your concentration is even better than exponential? Maybe then you can deduce that you have an even better than linear isoperimetric inequality. Okay, that's indeed the statement of our next result, which reads as follows. So assume now that our concentration function decays like exponential of minus some function alpha of r. And you can think that alpha grows at least linearly. Okay, so better than exponential. Then we obtain an isoperimetric inequality in the convex case, which is better than linear, v times some logarithmic improvement. Okay? And you see some constants here. The point is that both these constants are dimension independent. Okay, this is just some number, and here this is a constant depending very mildly on this function alpha. Okay? And if you check in examples, what happens, then it turns out that we really get the right isoperimetric inequality. So recall this two prototypical examples that we are considering. If we start off with alpha being quadratic in R, so if alpha is quadratic, then this just reads square root, so we get v times square root of log 1 over v. So really, we close the equivalence up to dimension independent constants in the convex case. Okay? So how about the semi-convex case? Okay, here the result is that a stronger than Gaussian concentration always implies a stronger than Gaussian isoperimetric inequality. Okay, so this is the statement. Assume, as before, we have our concentration assumption. But now, in addition, we're going to also assume that we have a growth condition on this function alpha. Alpha has to grow at least quadratically in R. And in fact, we're also going to care about this coefficient in front. The coefficient has to be kappa, where kappa is the same kappa from our curvature lower bound, times some constant delta naught, which we're going to assume is strictly bigger than 1/2. Okay? Then, under this additional growth condition, concentration implies back exactly the same isoperimetric inequality. It's exactly the same formula, the same, well, we get dimension independent constants, but of course the constants will now depend on the additional parameters that we added. Okay?
Half here is sharp, right?
I'm sorry?
Half here is sharp, yeah.
Yeah, it is. My next comment. Yeah. So exactly as Keith said. So, well, first maybe question that comes to mind that, okay, why did we need this assumption? In the convex case, we certainly did not need it. Maybe it's an artifact of the proof, but no, it's actually necessary, this growth condition. So it's necessary in the sense that our theorem says that whenever delta naught is bigger than 1/2, the concentration applies back the right isoperimetric inequality. But there's a sequence of examples constructed by Chen and Wang, even in the one-dimensional case, which they constructed spaces where concentration is satisfied with any delta naught strictly smaller than 1/2, but nevertheless no such isoperimetric inequality is possible. So really there's a sharp transition at 1/2. Okay? And actually it's very easy to explain intuitively why this happens at 1/2, assuming that this is what you meant maybe, remember that we have some curvature lower bound of the form minus kappa. And what is curvature? It's a second derivative type thing, right? So we need our concentration to be strong enough to compensate for the negative curvature. So this thing, if you take the second derivative, obviously you see that you get something which is strong enough. Okay, so this explains this 1/2. Okay. I stop at 3, right? Yeah, okay. Let me give you a quick idea of the proof. Okay, and contrary to other methods, which we're using semi-group tools, kind of heat flow techniques, or some techniques like localization technique developed extensively by Kahneman, Lovath, and Shimonovi, was rather confined to the Euclidean setting. So our method works on an arbitrary manifold and is completely geometric. Okay, and this is an approach set forth by Gromov in 1980 in his proof of the Gromov-Levy isoperimetric inequality. So this is how we're going to start. So we want to obtain a lower bound on boundary measure of a set having a given measure. So call this given measure V. Okay? So start with a set which is an isoperimetric minimizer. So a set in which this boundary measure is actually minimal. Okay? Now, a priori, it's not even clear that the minimizer should exist. Why should the minimum exist? You know, the profile is defined as the infimum. Certainly, we can take some sequence of sets which maybe converges to something, maybe not. So what we're going to do is we're going to use geometric measure theory, which was developed the second half of the 20th century extensively, which is precisely aimed at answering these types of geometric variational problems, as in our case. Okay, and you can see the list of many, a very partial list of many, many good and famous mathematicians that have contributed here. Well, let me just mention several of the founding fathers like De Giorgi, Federer, Fleming, and many others. Okay, so this theory, first of all, ensures that the minimizer does exist. Okay, that's kind of the easy part, actually. But moreover, it's going to tell us something about the regularity of the boundary of the minimizer. That's something which is actually more crucial for this approach. So here's a summary of what's known, what geometric measure theory gives us. So if you take this minimizer and look at the boundary of this minimizer in the interior of omega, okay, draw a picture maybe, then it can actually be decomposed. So this is our set omega, and we have some this is our set A. I'm deliberately drawing this for some reason. So you take the boundary of A, which lies in the interior of omega, okay, then it can be decomposed into a disjoint union of a closed singular part and an open regular part. Okay, so the bad news is that there may be a singular part, okay, but the good news is that this singular part is going to be small. Its Hausdorff dimension is going to be smaller or equal to n minus 8. In fact, this 8 is sharp. So it's not just a magic number appearing, there's a reason. So up to dimension 7, there will be no singularities. In dimension 8, you can already have some discrete set of singularities. So that takes care of the singular part. The regular part is going to be an open submanifold, a regular hypersurface. When I say regular, I mean it's going to be as smooth as our measure mu. So if mu is C infinity, then it's going to be C infinity. For our purposes, it's enough to take C2 because we just want to take 2 derivatives. So we have a C2 hypersurface. Okay? And if omega itself has a boundary, we're going to meet the boundary orthogonally. Okay? So actually, we're meeting the boundary here orthogonally, and this point is supposed to kind of depict an imaginary singularity. And all the other points are regular. Okay? This is actually the wrong picture, but I'm doing this deliberately. Okay, so now that we know that the singular part is so small, we can take just normal variations of the regular part. So we can just introduce some unit normal vector field here, exterior vector field, and start moving the regular part, start calculating variations. Since the singular part, we can go, since the singular part is so small, we can go all the way up to something like 7 variations of just the regular part, which will account for the variations of the whole boundary. Okay? Now, we don't need to go all the way up to 7 variations. For our approach, we just need to use the first variation. So, classical result in Riemannian geometry is that the first variation of a hypersurface is just what's called the mean curvature. So if you take the surface area of this hypersurface and you do this variation in the normal direction, you get the mean curvature, which is just, if you want, the trace of the second fundamental form. This is just a fancy way of saying that if you look at this point and you look at the tangent point to this point, it's well known that you can decompose the tangent space into n-1 principal directions, and with each direction there is associated a curvature, and the mean curvature is just their average. Okay, just by kind of approximating it by some paraboloid. Okay, so since our set solves some extremal problem, right? It's a minimizing surface area with respect to a volume constraint, then just by some Lagrange multiplier type argument, this means that the first variation has to be constant. Okay, so this means that we along the regular part, our mean curvature has to be constant. Actually, what I just said here for this line is when the density is constant. If we have a measure which is if you have a non-constant density mu, then you have to take the so-called generalized mean curvature, which also takes into account your density. But I don't want to give the formula. Let's just call this h sub mu of a. So we know that something is constant along the regular part, some parameter. Okay. Now the next thing that we would like to do is to employ, what we would like to really do is to bound from above the measure of an R extension. If this is a distance R, we would like to bound the measure of the R extension of the set A. Okay, one way to do this is, of course, you could try to integrate over the regular part, and you get these normal rays emanating from it, right? So you can try to control the Jacobian and try to integrate by Fubini. Do the integration here, do the integration here. If you can control the Jacobian, then you can get an upper. Well, you could bound this guy from above. The problem is the singularity here. Even a single point singularity completely destroys this approach, because as you can see, the normal rays will go in this direction, and you will completely miss this part. Right? This part will be completely missed if we're trying to do this approach. Okay? So singularities are a problem. So it seems that we're stuck, but here comes the beautiful observation of Gromov, which says that actually you can exploit the additional structure in the singularities of an isoperimetric minimizer and say that this cannot happen. Okay, so this is really the wrong picture. This point cannot be the singularity of an isoperimetric minimizer. So if you want to imagine how a singularity of a minimizer should look, the right picture to draw is the so-called double cone. This is the kind of the picture which you might want to keep in mind. Okay, so this point is singular. Okay, this is our kind of double cone, and this minimizer has the property that for any point outside this minimizer, the closest point to it on the boundary will always be a regular point. These are all regular points. So this point, this bad singularity, will never be the closest point to anything outside, right? Anything will always hit something regular before. Okay, therefore, if we take normal rays emanating from the normal part, from the regular part, we will actually sweep out everything. So,
in fact, if you had that previous picture, then even if it wasn't a singularity, such a shape would still mean you couldn't control the Jacobian.
you could, yeah. We'll see in a second that you could. So if I make this singular, and I can, because of this observation of Gromov, I can imagine that it's all regular, right? I can control the Jacobian. So it turns out, so you're bringing me to the next point. So I hope this addresses your question. If not, just ask again, okay? So this means that we can just integrate over the regular part, imagine there's no singularities, and just do this integration along the regular part, right? And we have to control the Jacobian. There's some classical theorems in Riemannian geometry that allow you to do that.
Yeah, that's exactly what I'm saying. The point is that if you can control the Jacobian, then in a sense you know that there's no problem with the singularities. Because if there were, it would look like a place where you couldn't control the Jacobian.
No. The Jacobian only depends on the intrinsic curvature of our manifold, which is controlled by kappa. That's our curvature lower bound. And on the mean curvature, which is constant. So actually, for this space, for this singularity, mean curvature is constant all the way here. The curvatures themselves are blowing up, but their sum, taking into account signs, not taking, so really the sum, the curvature individually could go to plus infinity, minus infinity, but they will cancel out. And their sum is going to be constant. So the second, so the Hilbert-Schmidt norm, sum of the squares is going to infinity here, but not the sum itself. It remains constant. Sorry?
I think you're saying the same thing.
Oh, okay, but in any case, so the Jacobian is controlled actually.
Yeah.
Okay. Even though there may be singularities, and you could be arbitrarily close to the singularity. Okay. So it turns out by classical theorems, and the one we're going to use is actually a generalization of the classical Heinz-Karcher theorem. This generalization is due to Frank Morgan. Turns out that this Jacobian only depends on the intrinsic curvature of your manifold, controlled by kappa, and an extrinsic curvature, which is controlled by our generalized mean curvature. Okay, so as we said, this guy is constant along all of the boundaries. So this Jacobian term just pops out. We just get this integration over the boundary times the Jacobian term. So we get the boundary measure of our set times this Jacobian term. So this is how we bound the boundary of this guy, the measure of this guy from above. To bound this guy from below, we can use our concentration assumption, exactly telling us that we're extending by at least something. And it looks like this is good news because we can bound the boundary from below, which is what we wanted. Right? We get a lower bound on the boundary measure of the set A. Now, almost, because we know what kappa is, but we don't know what this expression is. Right? This is essentially the mean curvature. It's essentially a Lagrange multiplier. We don't know how to control it. So this integral could really diverge. Okay, so what we do next is we do exactly the same thing for the complement of the set. We move to the complement of the set A. We do exactly the same thing. We get exactly the same bound. But now the only difference is that this thing becomes negative because we're looking at the set from the reverse side. So if this is large, this will be small, and vice versa. So we can win in one of these cases, we will win. Okay, and you have to do something else, and that's more or less the idea. This is how you obtain a lower bound on the boundary measure of the set, obtaining isoperimetric inequality. Okay, let me quickly say something about applications. Okay, and if you just take one thing from this talk, I hope it's actually this diagram. So we've seen that this always implies isoperimetric always implies Sobolev inequalities, which imply concentration inequalities, and under some curvature lower bound, we can actually close this diagram. Okay, of course we can recover all the previously known results, which were unfortunately dimension dependent. Everything for us works in the Riemannian setting. Let me skip over everything. I want to talk about stability of, let's say, Sobolev inequalities. Okay, so this is the application I have in mind. Assume that you have even space Rn, which you have some density on Rn. Okay, and someone comes and says, this density satisfies some spectral gap estimate or some log Sobolev inequality estimate. Okay, and now someone comes and takes your measure and perturbs the measure a little bit. Okay, and now the question is, does this new perturbed measure satisfy spectral gap or log Sobolev inequality? And if so, what's the relation? Can you quantify what happened as a function of the perturbation? And this is exactly, as far as I understand, the types of questions which are being asked in statistical mechanics, because there the density corresponds to some Gibbs measure associated to some Hamiltonian, okay? And the perturbation is, let's say someone is changing the temperature or flipping on some magnetic field. That's exactly the perturbation. And it's very important for statistical mechanics to know, first of all, to obtain dimension-independent bounds, because it's very important. Actually, the situation they're interested in is taking the limit when the dimension goes to infinity, because dimension corresponds to the number of particles. And taking the limit when n goes to infinity is exactly what's called the thermodynamic limit. Okay? And knowing that you have a uniform spectral gap estimate, for instance, is very intimately connected to the uniqueness of the Gibbs measure in the thermodynamic limit, the absence of phase transition. So this looks like a legitimate question to ask. So let's see what we propose to do. Okay, this is how we propose to attack the question of stability. Analyzing stability on the Sobolev level, unless the perturbation is kind of trivial, looks rather difficult. Okay, so instead of doing it directly on the Sobolev level, here's what we suggest. So you can always go down to the concentration level, right? This is always true, without any assumptions. So take your, go down to the concentration level and analyze the stability on the level of concentration. Concentration inequalities are much more robust. Okay, they don't care what happens on infinitesimal extensions. Turns out that on this level, it's very easy to analyze stability. Okay, it's essentially an exercise. And then, if you're lucky enough that after the perturbation, the perturbed measure satisfies some semi-convexity conditions, you can just go back the hierarchy and obtain the desired stability on the Sobolev level. Okay, so it's a very simple idea, but actually works. So let's see an example. Assume that we have two probability measures on, let's say, our n, even though you can do it differently on manifold. Let's assume that they're log concave, so the potentials have to be convex. So the first result is that if the total variation distance between these two measures, which is just 1/2 times the L1 norm of the difference of the densities, if this, well, of course, the trivial bound of this by the triangle inequality, since these two things are probability measures, the trivial bound is that this is bounded from above by 1, by triangle, right? The integral of each of these is 1. But let's assume that you know it's 1 minus epsilon, positive epsilon. Then, if the first measure satisfies the spectral gap inequality, so does the second one, and of course dimension independent, and you can analyze the stability with respect to the parameter epsilon, and then you actually get essentially the best possible dependence up to dimension independent constants. Okay, so you get stability. You can do this not just with total variation, you can do this with relative entropy, you can do this with one Wasserstein distance, many things here work. The point is that this is completely false without the convexity assumption. Okay, there is actually no stability for spectral gap if you don't assume something about curvature. And maybe my favorite application here is just something in geometry, right? You want to analyze the spectral gap of a perturbed domain. So let's say you start with the nicest domain of your choice. Let's say Euclidean ball. Okay, you know the spectral gap here for this Euclidean ball is just zero of some Bessel function. And now some adversary comes and starts really deforming, cutting away pieces from this Euclidean ball. Maybe adding pieces, but in a way such that the resulting new domain is still convex. Okay, and then the result is that as long as the overlap, just this part, the part where these two original domain and perturbed domain overlap, as long as in terms of volume the overlap is big enough, let's say 1% of each of these two domains, then these two domains, original or perturbed, have essentially the same spectral gap, up to a factor of, let's say, 1,000, independent of dimension. So in other words, in the convex category, convex domains, it's the spectral gap does not depend on geometry if you're already in the convex category. It just depends on volume overlap. Okay, which might be surprising, at least it was surprising for me. Okay, and this has been used by various people. You can do the same for log Sobolev inequality. Let me not talk about that. When do you have like what just? Yeah, thanks. So here's another application for in the compact case. Okay, remember this, we said that any compact space has a great concentration inequality, right? Because if the diameter of the space is d and we extend beyond this diameter, then there is nothing left outside. So in terms of concentration, we have great concentration. So you can just apply our result to the concentration bound, the trivial bound. So 0 if we extend beyond the diameter d, and before the diameter d, we have no information. We don't know what's going on, so we just give it some trivial bound like 1/2. Okay? So use this. So assume that we're also in a situation where our semi-convexity assumptions are satisfied. Ricci plus Hessian is bigger than minus kappa. Okay? Plug this into our main theorem. You get some formula, and you obtain an isoperimetric inequality, which is dimension independent. And the constant here will depend only on the diameter d on the curvature lower bound kappa. Okay? This is the form you will have. So it's dimension dependent, and in fact, if you check in examples, it's actually best possible with respect to kappa in D. Okay? And also, if you're already in the isoperimetric level, you can go down to the Sobolev level and see what happens on that level. So you can try to go down to the Poincaré, to the spectral gap estimate level. And in this case, we actually essentially tie up to constants the best known result, which is due to Chen and Wang. Okay? And on the log Sobolev level, you can go down to the log Sobolev level and actually improve at least what I know was the best known results, best known results in this setting, due to Wang and Bakri-Leduc. Okay, so just for free, you have a concentration, plug it into the theorem, you get these results. One last thing I would like to mention, maybe as I conclude, all of what we're saying here is up to constants, right? Up to numeric constants, dimension independent but numeric constants. If you do things more carefully, you can actually obtain sharp isoperimetric inequalities on compact manifolds. So this is a new result from this year. So assume now that we have this curve. So assume that our measure on our manifold has density, which now I'll call phi. Okay, and assume that we have a certain curvature lower bound on an even more general tensor than Ricci curvature, given by rho, where rho now is an arbitrary real number. Could be positive, could be 0, could be negative. Okay. So this more general Ricci curvature, let me not, this is the formula. Let's not dwell on the formula. In some sense, it just interpolates between the case between 0 and infinity. When this parameter q is 0, then this generalized Ricci curvature just degenerates to the usual Ricci curvature. So this corresponds to the case where the density is constant, just Riemannian volume. And when q equals plus infinity, we just get the Ricci curvature, which we've seen throughout this talk, Ricci plus Hessian. Okay? And there's some intermediate values you can also treat, but let's just stick to 0 and plus infinity. Then the result is that we have the following: for such a space, having diameter in addition bounded from above by d, for such a space, we actually obtain an isoperimetric inequality, in which, let me just read it out. You have to take some infimum over a 2-parameter family of parameters, and this isoperimetric inequality is modeled on the interval of length d on the real line. And what is the density you have to take on this real line? Is just this density, where the functions c delta and s delta are just the usual functions in Riemannian geometry. Cosine if the curvature is positive, and hyperbolic cosine if the curvature is negative. Okay, so you take this density. It doesn't integrate to 1, so you just normalize it on this interval and you make it probability density. And this becomes your model density. You calculate the isoperimetric profile for this density, and you get a function on the interval 0, 1, and you take pointwise infimum for all these functions on these 2 parameters. Okay? So this is a completely general description for all possible values of rho, d, and q. Okay? And the main interest in this result is that it turns out that this is a sharp lower bound. You cannot improve for any n-dimensional manifold, you cannot improve this result. And in particular, this means that we must have recovered the sharp classical results due to Gromov-Levy and due to Bakri-Leduc. So indeed, this is the case. We recovered the result. And these cases, actually, you can simplify just by using some, this is cosine, this is sine. You're using some algebraic properties of sine and cosines. You could just simplify this expression. And in many cases, this 2-parameter infimum just degenerates into a concrete density. And indeed, we recovered the result of Gromov-Levy, because if you use q equals 0 and curvature is strictly positive, the density you recover is actually just sine raised to the power of n minus 1. Okay, and if you think about this, this means that this one-dimensional density, this is exactly the density, this is exactly the isoperimetric profile of the n-dimensional sphere, because their geodesic balls were minimizers. So if you project onto this direction, you get exactly the sine density, sine to the power of n minus 1. We recovered this Bakri-Ledoux result because then the density degenerates to the Gaussian density. Okay, in all the other cases, actually, there's no degeneration. You still have to take an infimum over a one parameter family of parameters. Okay, so all the other cases are actually new, and maybe the reason that they were not discovered is because there's no one model space to compare to. Okay, so in all the other cases, there's no single model space to compare to, but actually a continuum, a one-parameter continuum of model spaces we need to compare to, and you just have to pick the worst one, and that's the sharp isoperimetric inequality that you get. Okay, that's the fact of life. So, let me just leave you with this slide, which sums up the talk, and thank you for your attention.
One possible way of thinking about why some spaces are hard is that if you take a minimizer at one probability and a neighborhood of it, and you don't get a minimizer at the new probability, there's something a little bit strange happening.
Could you repeat that? You're taking a minimizer.
So in simple spaces like Euclidean space, you take a minimizer, you expand it, what you get is a minimizer for a bigger probability, or bigger measure. Now, is it the case that the failure of that is somehow what underlies it is?
Yes. So indeed, the point is that this infimum over this one-parameter family, so it's a pointwise infimum. So these functions are functions on the interval 0, 1. So if you want to know what the worst boundary measure of a set is, having a measure 1/4, you take this 1/4. This infimum is going to be attained at some parameter. You move this 1/4 to 1/4 plus epsilon, this infimum is going to be attained at some other parameter. Yes?
Questions? Well, thank you again.